Space doesn't tear itself apart because of rules you can't see. They run quietly inside every atom and across galaxy clusters. The immediate takeaway is simple: symmetry and feedback keep physics consistent. You will hear how clocks, fields, and gravity agree everywhere. Quick example: GPS works only because these rules sync every tick. So the picture is, hidden rules quietly stabilize reality at every scale. Stand beneath the 27-kilometer ring of the Large Hadron Collider. You feel Earth still, yet protons scream by at terrifying speed. Symmetry, in plain words, means physics looks the same after changes. This matters because sameness across shifts locks in conserved quantities. Noether connected those symmetries to energy, momentum, and charge. Here is the core move: treat a transformation like sliding or rotating. If the equations do not blink, a quantity cannot drift. Energy holds steady over time because time shifts change nothing important. Momentum holds steady in space because sliding the stage changes nothing. Charge holds steady locally because tiny phase twists cancel themselves out. Rule of thumb: symmetry is a promise that books will balance. Detectors around the ring add every fragment after a collision. The totals match within tiny uncertainties across millions of recorded events. Example: in real terms, two protons smash and spray 100 tracks. Add every vector, the sum points almost exactly along the beam. Add every bit of energy, it agrees within fractions of a percent. Even messy debris respects the bookkeeper, and that keeps theories testable. Bottom line: sameness under change forces conservation, and conservation forces consistency. Now hold a fingertip over a ticking atomic clock on a satellite. Every tick agrees with ground clocks only after relativity corrections. Lorentz invariance says the laws stay identical for all constant motions. You care because cause and effect need a universal ordering. Without that, signals would cheat, and experiments would contradict themselves. Here is how it holds: the speed of light caps information flow. Spacetime mixes space and time so moving clocks appear to slow. Rulers shrink along motion, while intervals rotate between time and distance. Tiny test: two observers swap light pulses and compare round-trip times. They compute identical physics, even though their clocks disagree about durations. GPS rides on this framework with ruthless precision every single day. Satellites orbit about 20,200 kilometers above Earth, moving at great speed. Gravity speeds their clocks, motion slows them. Net drift is 38 microseconds daily. Engineers pre-adjust the onboard frequency so receivers see perfectly synchronized time. Phones on the ground then locate you within a few meters. That accuracy vanishes instantly if Lorentz symmetry gets even slightly bent. Net result: a cosmic speed limit quietly keeps experiments logically consistent. Drop a hammer and a feather inside a giant vacuum chamber. They fall together while the floor rushes up to meet them. Equivalence says free fall cancels gravity, leaving only local straight motion. You should care because this turns gravity into smooth geometry. That shift lets clocks and rulers behave predictably near massive bodies. Mechanically, free objects follow geodesics, the straightest paths through curved spacetime. Mass and energy bend spacetime, and bent spacetime guides further motion. Light follows those curves too, even though it has zero rest mass. Example: in real terms, a galaxy cluster acts like a glass lens. Background galaxies stretch into arcs, sometimes magnified by factors near 10. The cluster Able 1689 shows dozens of arcs across a wide field. Those arcs let teams map mass, including dark matter that emits nothing. Measurements then agree across wavelengths, from X-rays to infrared emissions. Rule of thumb: wherever lines bend, a gradient of gravity is present. Astronauts floating in orbit feel weightless, yet follow Earth's curved geodesic. Their path wraps the planet every 90 minutes at great speed. So the picture is, gravity behaves like geometry, not a tugging force. Pan out to the largest map ever stitched from ancient light. The microwave sky glows with grains barely colder or warmer than average. Cosmologists assume the universe is homogeneous and isotropic on huge scales. You should care because that lets one set of equations describe everything. Inflation explains why this looks true by stretching early wrinkles almost flat. Quantum jitters froze into seeds, while expansion blew them up enormously. Afterward, gravity amplified those seeds into galaxies and clusters we see. Crucially, the average stayed uniform to shocking precision across the entire sky. Numbers help: temperature varies only by 1 part in 100,000. Polarization patterns align with that story, down to tiny angular scales. Distances inferred from ripples match supernova data within a few percent. Quick check, random spots differ a hair, yet statistics match spotless predictions. That consistency is not a coincidence, it is a built-in mechanism. Example in real terms, two opposite patches differ by microkelvin amounts, but their power spectrum matches the curve predicted by a simple model. Telescopes in deserts and balloons confirm those peaks again and again. Bottom line, large-scale sameness with tiny seeds keeps cosmic history computable. Slide down from galaxies to the quiet interior of an atom. Nothing sits still there, yet matter does not collapse or explode. Quantum fields set the rules by which particles appear and interact. You should care because stable matter is the start of everything. Electrons fill orbitals because the Pauli principle blocks identical crowding. That blocking pressure scales up to support stellar corpses against gravity. Meanwhile, fluctuations fizz at every point, creating pairs that cancel on average. Renormalization resums the mess so predictions land on finite numbers. When fields are arranged consistently, infinities fold away like balanced debts. Tiny tests squeeze matter and watch pressure rise without heating first. That is degeneracy pressure, a quantum effect with very real heft. Example in real terms, a white dwarf weighs about 1 solar mass. Its radius is Earth-sized, despite a million times greater density. Push harder above about 1.4 solar masses, electrons finally give up. Gravity then wins and triggers collapse, often toward a neutron star. Even there, quantum rules shove back, with neutrons providing the support. Net result, exclusion and vacuum bookkeeping quietly prevent runaway catastrophe in matter. Step inside a cavern where a particle detector hums like a city. Cables spider everywhere, while chilled magnets hold near unimaginable fields steady. Gauge symmetry is the idea that certain relabelings change nothing observable. You care because that protects charge, forces, and probabilities from nonsense shifts. Local phase twists generate electromagnetism, while non-abelian twists generate nuclear forces. Change the labels smoothly, and compensating fields keep predictions identical. Equations then insist that charge is conserved in every tiny region. Common mistake is thinking symmetry is decoration, rather than a constraint. It is more like grammar, rejecting illegal sentences before they exist. Example in real terms, detectors count equal charges before and after collisions. Atlas alone reads over 100 million channels during busy runs. Events with leptons and jets still balance electric charge to machine precision. Data pipelines flag rare outliers which almost always trace to sensors. On long baselines, thunderstorms shuffle coulombs, yet total charge remains unchanged. Even batteries respect the budget, separating charge without deleting or creating. Bottom line, gauge freedom demands bookkeeping, and bookkeeping forbids physical contradictions. Watch a massive galaxy glow while a black hole fires a steady jet. The core seems tiny, yet it controls gas across the halo. Feedback is the loop where stars and black holes throttle fresh fuel. Care because without regulation, galaxies would burn gas in a flash. Supernovae push and heat clouds, stirring turbulence and raising pressure against collapse. Jets from central engines punch cavities, lifting hot plasma through the core. Shocks and waves spread energy, preventing dense cooling at the center. Meanwhile, gravity keeps trying to gather gas back toward star formation. Example in real terms, the galaxy M87 launches a bright relativistic jet. Its black hole weighs about 6.5 billion times the Sun. X-ray images show bubbles tens of thousands of light-years across. Those bubbles match the power needed to offset the cooling flow. Simulations that remove feedback form stars at least several times too fast. Add feedback, and star formation settles near observed values across epochs. Rule of thumb, galaxies behave like thermostats set by delayed energy bills. Even messy mergers eventually relax because the budget always gets balanced. Net result, quiet loops between explosions and gravity keep structures from overshooting. Shift to a spiral galaxy where stars trace glowing circular lanes. They orbit so fast that visible matter alone cannot hold them. Consistency here comes from invisible scaffolding we call a dark matter halo. You care because that scaffolding sets stable orbits for billions of stars. Inside the halo, gravity and motion reach a statistical standstill called virialization. Kinetic energy balances half the binding energy, keeping the structure from collapsing. Outside the halo, space itself expands, stretching paths between galaxy groups. Dark energy accelerates that stretch, while gravity fights to keep neighbors bound. Example in real terms, the Sun orbits around 220 kilometers per second. Its distance from the center is about 8 kiloparsecs, give or take. Those numbers only make sense if a massive halo surrounds the disk. On larger scales, the Hubble rate sits near 70 kilometers per second per megaparsec. Pairs beyond several megaparsecs mostly drift apart, riding the expansion like rafts. Yet the local group stays bound because gravity beats expansion nearby. Quick guide: inside halos you get orbits, outside halos you get flow. Bottom line: scaffolding and stretch together set where things stay and where they go. Zoom back to the night sky, steady and wild at once. Clocks agree, charges sum, and orbits hold without fanfare. These are not decorations, they are the quiet wiring of reality. If you want more deep dives like this, feel free to subscribe. We can keep unraveling how hidden rules shape visible wonder together. Bottom line: space stays consistent because symmetries and feedback never stop working.